Well, now we're going to use this framework we've built up to take a look at an extension of an infinitesimal line element. So I have my two bodies here, region R and region script R, the original and the deformed configuration, and I've got a couple of points labeled in each. Point P, regular P, is located at the ordered triple x1, x2, and x3. And a short distance away from point P is point A. It's a very small distance away. I have to draw it as if it's a finite distance away, but it's really just a little bit further along, like x1 plus dx1, x2 plus dx2, and x3 plus dx3. Now over in the deformed region, this is what we're going to use our symbol xi for, like we've been doing. We have script P, which is a mapping from regular P to script P over here. And that point is located at xi1, xi2, xi3. And script A is a little bit away from it. The infinitesimals are a little bit different in general. But xi1 plus dxi1, xi2 plus dxi2, and xi3 plus dxi3. Now the distance between point A and P, we're going to call the distance ds. That's our regular s, lowercase s, and it gets deformed, and the distance between these 2 points now becomes a little bit different. I'm going to call it d script s. And lastly, we're going to define a unit vector that goes from the direction of A to P, or from P to A rather. The unit vector we'll call regular N, and his components N1, N2, and N3. This will be a unit vector, and likewise, that gets changed. It points off in a new direction over here. We call the script N, and it has components script N1, script N2, and script N3. Well, we can draw a vector between A and P. That vector with the little squiggle underneath of it is determined by the coordinates of point A, subtracting off the coordinates of point P. And if we do that, then we would have this little vector here that has components dxi. Let's write it this way. In the ijk coordinate system, we'll say that it is dx1 in the e hat 1 direction plus dx2 in the e hat 2 direction plus dx3 in the e hat 3 direction. Or we can think of this as I, j, and k if we would like. We can find the distance in between the two. In fact, the square of the distance in between, there's no squiggle underneath there, that's a scalar, would be the magnitude of that vector, ds with the line under it, squared, which we can find, we talked about our dot product previously, by ds dot ds, which would be dx1 squared plus dx2 squared plus dx3 squared, or we can say this is equal to dxi dxi by the use of our index notation. And in a similar fashion, we can go through and we can find d script s, that magnitude squared. You need a square right here. That d script s squared can also then be found by d xi, or we can use any other dummy variable that we want. Remember, when the index is repeated, that's a dummy index. So we could just as easily write down d psi k, and that is the distance squared in between point script P and point script A. We've talked about admissible deformations. If the deformations are admissible, then these relations are invertible. The transformations from regular, the undeformed to the deformed space, and their derivatives exist. We're not allowing for any continuity issues in this continuum assumption. Let me make a little bit of room here. We've talked about the total differential already, but for example, total differential d psi 1 is determined by the rates of change of psi 1 with respect to the spatial coordinate, the partial derivative psi 1 with respect to x1, times the amount of distance that we go in direction 1, so dx1. And likewise, we need to add in the effects from the other two directions on that one component for xi. So it's partial psi 1 with respect to x2, dx2, and then the partial derivative of psi 1 with respect to x3, dx3. Now we can have two similar relationships for d psi 2 and d psi 3. If we want to generalize this with our index notation, we can say that for any d psi I, we can write down the partial derivative of psi I with respect to xj, dxj. Okay, so you see how this works out? Okay, notice this is the one component here, and then this is the repeated component for that summation. So now we have a summation over this dummy index j. And the I in this case would be what's called the free index. Now we could also use our comma notation to denote partial differentiation. And this then would be xi I, comma j, dxj. Same thing. Now we had our relationship for the displacement between 2 points. The displacement component ui is the final minus the initial position. Or if we want to find the final position, we can say the final position is the initial position plus the amount of displacement of that particular point. So now that we know what an expression for xi is, we can put that back into here and write d xi I is the partial derivative of this quantity xi plus ui with respect to xj, dxj. And multiplying that term out, we would have the first term, the partial derivative of xi with respect to xj, plus the partial derivative of ui with respect to xj, and then we would have our dxj out here and back. Now the first term we've seen a few times already, that's their Kronecker delta. Let's write it this way. That would be Kronecker delta ij. As just a refresher, when I and j are equal, that evaluates out to be 1 they're equal to the same index. When I and j are different indices, for example 1 and 3 would be different indices, and that term evaluates out to be 0. So that'd be Kronecker delta ij plus partial derivative of ui with respect to xj dxj out on the side here, or again with our comma notation for partial derivatives, we can write this as Kronecker delta ij ui comma j dxj. Okay, so again, this is a way to write the total differential. Let's make a little more room. Alright, so we got that up to the side there. Just we'll keep that in mind for a moment. And now we're going to look at the change in the square of the lengths. It's going to be a little bit more convenient to look at the square of the length than it will be the actual length, and we'll see why in just a moment. But what I mean by that is, remember we had our original and our final length between the points A and P. In the final configuration, we called that length ds. So the square of that length is d script s. And in the original configuration, the distance in between points A and P was ds, and so the length squared is ds squared. So the change in the square of the lengths is d script s squared minus ds squared. Now we know that we can write d script s based on our dot product, and we saw how we did that. In our index notation, we can use any two dummy indices. So we have d xi l and d xi l, for example, where l is the dummy index. And we can also have any dummy index we want over here for d regular s squared. So let's see how I've written it. I've written it as dxk dxk. Remember, we're free to choose any dummy index that we want. It's probably not a good idea to use L in 2 pairs or K in 2 pairs. So I've just chosen L and K separately here. Could have used M or N or anything like that. Alright, so we just saw how to find d xi I. So let's write down what d xi L would be equal to. I'm going to try to be really careful here so I don't mess any of these terms up. So d xi L, okay, instead of I, we're going to use L. So this would be Kronecker delta L j plus U L comma j dxj. And we have one more just like it to represent the second term. Kronecker delta L j plus U L comma j. Now I can't use j. I've already used it in this pair. I'm just going to have to use something else. How about I use I? Haven't used it yet. So Kronecker delta Li UL comma I dxi. Right? So all of this right here represents this first term that I have, and then I need to also include the second term dxk dxk. Okay, now the Kronecker delta and the deformation gradient term, those all represent second order tensors. Here's where we can see the real power of our index notation. We can treat these quantities very algebraically with a few rules thrown in. So I'm first going to group the two dx terms together, and I'm going to group the terms in the brackets together. And then plus U L comma j, and the second term, Kronecker delta L I plus U L comma I. And now we're going to have the dxi and the dxj term. I'm just going to write them in that order. Can write them in the other order if we want, but that's okay. And then dxk and dxk. Alright, now we can algebraically expand these two expressions in the brackets. Alright, so let me take the first one. I'll write it this way. Kronecker delta Li, Kronecker delta Lj, plus Kronecker delta Lj, Ul, comma I, plus Kronecker delta Li, Ul, comma j, plus Ul, comma I, Ul, comma j. We have the bracket, then we have the dxi, dxj, then minus dxk, dxk. Alright, now we know that we can use the Kronecker delta as a replacement operator on indices. Just to review, when we have an index in common with a Kronecker delta in any other term, doesn't have to be another Kronecker delta, what we can do is we replace that repeated index with this index right here. Okay, so on our first term, we have Kronecker delta I, j. And you see I replace the L right here with this I. On this next term, we have Kronecker delta Lj. So I'm going to write this as U, j, comma I. This third term, U, I, comma j. There's no Kronecker delta in this term, so I have to keep that Ul, comma I, Ul, comma j. Then we have the dxi, dxj, then minus dxk, dxk. Alright, now I'm going to do one more thing. I'm going to take and I'm going to distribute this term with the first term. So I'm going to have a Kronecker delta ij, dxi, dxj. I'm going to leave these terms in the brackets. I'm going to rewrite them in a little bit different order that's a little bit more standard. I, comma j, plus u, j, comma I, plus this term, ul, comma I, ul, comma j. Those are subscripts. And then here I have the dxi, dxj, and then minus dxk, dxk. Getting a little tight on space. Let me see if I can move this little window, little toolbar here. Okay, now we have a Kronecker delta multiplied by some terms here, and again we see there's a repeated index. So I can rewrite this and can eliminate the Kronecker delta, and I can rewrite this as a dxj, dxj. And you see the repeated index was I on these two terms, so that becomes a j, and then we have the other dxj right there. Okay, now I'm also going to write this term, the last term, right here, and then I have the term in the brackets. I'll try to write it real quick. If we look at this very carefully here, the j and the k on those terms are repeated indices. Those are dummy indices. That means we have an implied summation, so that's a dx1 squared plus dx2 squared plus dx3 squared minus the quantity dx1 squared plus dx2 squared plus dx3 squared. These are the exact same terms. These will annihilate each other. Those will cancel each other out. So the change in the square of the lengths can be rewritten as this expression right down here. Let's get a clean page and make a little bit of room. Alright, so let's take a look. So we have the change in the square of the lengths, d script s squared minus ds squared. It's equal to this thing in the brackets times dxi dxj. So remember what dxi and dxj are. Right now, for us, the way that we're going to interpret the dxi is it's the distance between those 2 points, A and P, in the original coordinate system, the undeformed state. And these displacement rate terms are right here. It's the partial derivative of ui with respect to xj plus partial derivative of uj with respect to xi, and then we have these terms right here. So these displacement rate terms, spatial rates, not time rates, these displacement rate terms have something to do with deformations and the rate of displacement. We're going to define this term as 2 epsilon ij, and then these two terms right here, dxi, dxj, will be out to the side. Now, if we look at this term very carefully, we'll notice that with epsilon ij equal to 1/2, partial derivative of ui with respect to xj plus the partial derivative of uj with respect to xi plus this term right here, partial of ul with respect to xi plus the partial of ul with respect to xj. Okay. There's no plus sign right here, sorry. On this last term, there's a repeated index of L. There is an implied summation. And if we were to replace the subscripts I and j, then this thing, it's going to be a second order tensor, this thing is symmetric. Okay, it's symmetric. It's going to be a second order tensor because this displacement gradient is a second order tensor. Now it's also dimensionless. The epsilon ij is dimensionless. See, the units are all tied up in the dxi dxj term, and that'll give us the square of the length type units. We will again, I'll just mention it again, we're going to go through and formally define second order tensors, and we'll show how it is a second order tensor. But for right now, take my word for it that since our displacement gradient terms are second order tensors, this is a linear combination of second order tensors. It is a second order tensor, so this epsilon ij is a second order tensor. And this has a particular name. Epsilon ij is called the Green-St Venant Strain Tensor. There are a couple things to note about it. These terms are defined in our original coordinate systems with these x's, these x sub I terms. We could have gone about this the other way and used our reference configuration as the final deformed state. I'll show you what we get when we do that in just a moment. But for now, we're going back and looking at our original state. You're probably familiar with engineering strain, where we have strain defined as the change in length divided by the original length. And that's fairly analogous to what we have here. Of course, you could think of strain in a different way. You can say it's the change in length divided by the final length. Okay, well, then you'd have something a little bit different, but it's still kind of a measure of strain. It just depends on what you're calling your reference configuration. And that's what we'll get when we'll talk about something called the Almansi strain tensor. But for right now, let's work with this just a little bit. This is a very interesting thing that we have right here. And there's a lot of information packed inside of this term. Okay, so what we're going to do is we're going to expand a few of these terms out, get a feel for what this looks like. Now, one of the things I want to point out is when we did all this math, we haven't done any approximations of anything. There's no Taylor series expansions or truncation of higher order terms or anything. This is the full thing. This is the whole deal right here. All right, let me save this page and let's expand a few of these terms out in this strain tensor. This 2 in this term gets to be a little bit awkward at first, but we'll kind of work through things here and see how that works out. So we have this expression is equal to these displacement gradient terms, dxi, dxj. Another way we can write this is then if we divide both sides of this term by 2, we can have on the left-hand side 1/2 d script s squared minus d regular s squared is equal to this thing epsilon ij dxi dxj. And if we want, we can expand this term out on the right-hand side, because if you see here, there's a double summation. Both I and j repeat. Now I goes from 1 to 3, j goes from 1 to 3, so we end up having 9 terms. Let's write them all out. We've done this a couple times already. But we'll start with 1 and 1, and then we'll leave the first one as 1, and then we'll make the second one 2, and 3, and so forth. Now these are all added together. What we end up with is a scalar quantity. And it makes a whole lot of sense, because if we think of the left-hand side, that is obviously a scalar quantity because we're measuring distances. There's the difference between the square of the distance, but they're distances nonetheless, and that's a scalar quantity. So let me go ahead and write this down. Sometimes when I write and talk at the same time, I can mess up my subscripts, so do keep an eye on me. I will try to correct anything that I see, but every once in a while there are things that will slip past me. So keep me honest and keep an eye on my subscripts. And we have the last one, epsilon 3 dx3 dx3. Now since the tensor is symmetric, we can do a little bit of manipulation with this. We can lead off with our 3 terms that look like the 1, 1, the 2, 2, and the 3, 3 terms. Tell you what, let's go ahead and write this as a squared right here. Okay, epsilon 2, 2 dx2 squared, epsilon 3, 3 dx3 squared, and then since, let me use a different color, since this term and this term are the same because of the symmetry, then epsilon, we can write this as 2 epsilon 1, 2 dx1 dx2 and 2 epsilon 1, 3 dx1, dx3 into epsilon 2, 3 dx2, dx3. Okay, so we have this thing, this strain thing with all these components in it, and somehow when we multiply that strain thing times these squared infinitesimal lengths, or combinations of them, dx1, dx2 for example, we end up being able to figure out what the change in the square of the length is between the deformed and the original configuration, with a factor of that half thrown in there too. Okay, so it's definitely a measure of some sort of distance that goes on in between the original and deformed configurations. Well, maybe it doesn't make a whole lot of sense right now, but as we go through this in a little bit more detail, we're going to be able to shed a little bit more light on what this thing is called the strain tensor. Well, let's look at the individual components of the strain tensor now in terms of these displacement rates or displacement gradients. So let's start off with epsilon 1, 1. Okay, that's a half. If I is 1 and j is 1, we have partial derivative of u1 with respect to x1, and then we have that exact same term again. Now here's where I have to be a little bit careful, is on this third term, there's an implied summation between, on this L, this dummy index L, I and j are going to be fixed at 1. So there's actually 3 terms in this next expression that we're going to write out longhand. We get the partial of u1 with respect to x1 times the partial of u1 with respect to x1. The I and the j are both 1, but we're going to increment this index. So now we're going to have plus partial of u2 with respect to x1, partial of u2 with respect to x1. And then one more time, one more incrementing, the partial of u3 with respect to x1, partial of u3 with respect to x1. We also have 2 more similar terms. I'll probably ask that you go ahead and write these out on your own. Epsilon 2, 2 and epsilon 3, 3. Let's do one more just so you get the hang of it. We have the half out in front. Now u2 with respect to x2 and u2 with respect to x2, partial derivative there. Now we have plus. Okay, now remember the L is the dummy index, so we have the partial of u1 with respect to x2, partial of u1 with respect to x2, partial of u2 with respect to x2, partial of u2 with respect to x2, and the partial of u3 with respect to x2, and the partial of u3 with respect to x2. Okay, so those are all the terms there in that strain quantity. I'll let you do the third one. We also have some terms that look like epsilon 1, 2. Let's write out one of those. We have half, and now in this case, I is 1 and j is 2. So we have partial derivative of u1 with respect to x2, plus partial derivative of u2 with respect to x1. And now here I have to be a little extra careful. Again, we're incrementing the L, that's the dummy index. So we have plus partial derivative of u1 with respect to I equal to 1, partial derivative of u1, and then j is equal to 2. Now we make this the u2 terms, and then finally the u3 terms. With respect to 1 and 2. And I'll let you finish these other 2 out. All right, let me make a new page. Okay, so let's go back and write down the change in the square of the lengths again. Now remember when I said we could write these two terms both in terms of the x or the xi. If instead we write everything in terms of the xi, we can end up with an expression that looks very similar. I'm going to use like a script epsilon right here. To script epsilon ij, then we have a d xi I and d xi j. Again, this is analogous to, instead of using the change in length divided by the initial length, if we were to use, say, like the change in length divided by the final length to come up with some sort of strain or measure, then that would be analogous to this. In here, the script epsilon ij would be equal to 1/2 we would have the partial derivative of u sub I with respect to xi j plus the partial derivative of uj with respect to xi I, and then minus, instead of plus, partial derivative of ul with respect to xi I times partial derivative of ul with respect to xi j. And this is known as the Almansi strain tensor. Now, I'm not too concerned about whether or not you remember the names Green-St Venant or Almansi strain tensor. If you work with these enough, you will remember those. But the important thing I want you to get out of this is that one is based on the original configuration and one is based on the final configuration. The Almansi strain tensor is often known as the spatial version of the strain tensor, whereas the Green-St Venant, the epsilon that we had defined earlier, is the material or the Lagrangian version. Now, often what I do is I would ask students to derive this for a midterm question or maybe a homework question. And I like to ask that because it's pretty straightforward. It is a little bit different than what we did for the Green-St Venant strain tensor. And it goes through all the same steps, except we have that minus sign. And it's pretty easy to see where that minus sign comes from if we think about it. Remember when we said that the final position was equal to the original position plus the displacement? Well, if we write everything in terms of x instead of xi, then what we're going to have is the original position is equal to the final position minus the displacement. Okay, so that's exactly where that minus sign will come from. But I'll let you work through those details, and probably should be expecting that either on a homework or on a midterm type exam question. Alright, well, the rest of what we're going to do, talking about the Green-St Venant strain tensor anyway, is try to put some perspective on what all this means. We've done the math, now we need to give some physical interpretation of this. And for that, what I think I'm going to do is I'm going to stop this video, I'll call this part A, and then we'll pick up with some physical interpretation of this as part B. We're first going to take a look at extensional strains, and then we're going to take a look at shearing strains.